All right, today we're going to talk about energy and matter and some of our nutrient cycles that we need to know about. Some vocab that you need to know: gross. Anytime I say gross, it's not like, ew, gross. It's gross as in the total amount. So when you get your gross pay on your paycheck, that's your total amount. Net is the amount after deductions. So on your pay, you're going to have a gross pay and a net pay. So my gross pay is $13,000 a month. My net pay is $10,000 a month. Well, what happened to $3,000 of it? That was all the deductions for taxes and Medicare and health insurance and the union and all of this other stuff. It's depressing, but it is what it is. When we talk about plants, gross is the total number or amount of photosynthesis that plant did. Net is the amount of photosynthesis that plant did minus how much respiration the plant did, how much it used for its own benefit. Net is what's available to go up to the next rung on the food chain. Primary is plants always. Secondary is animals always. Gross productivity, or GP. This is the total gain in energy or biomass per unit area per unit time. You guys need to know that those are the units, right? So per unit area per unit time. Remember, biomass is the weight of the living things minus the water. This is the total present before respiration. Net productivity, or NP, is the total energy left after respiration per unit area per unit time. So this is how much energy is available to go to the next rung of the food chain. Gross primary productivity is GP, or gross productivity, in green plants or algae. It's the energy that's brought into the food chain through photosynthesis, through the conversion of sun energy into sugar energy. And it does not subtract out the plant or the algae's own needs. Net primary productivity, or NPP, is the amount of energy left after plants and algae have taken care of its own life needs, after they've grown, after they've moved, after they've done whatever it is that they need to do. This is the amount available for the next link in the food chain. The fate of energy reaching the earth. So we have the sun beating down on us on all times, and it's going to hit a leaf on a plant. 5% of the solar energy that hits a leaf immediately is bounced off and reflected back. This is what the green color is, right? That's the color reflecting back to your eye. 5% is actually going to pass all the way through the leaf. So the leaf isn't going to use it. It's just going to go right through it. 50% is just lost, right? So it hits the leaf, but the leaf has enzymes that are fully functional and are busy, and so it can't use it at that time, or the material is not right to do photosynthesis at that time, or the temperature is not right, and so 50% is just lost. 40% of the sunlight that hits a leaf is actually absorbed by that leaf in the photosystems. Of that 40%, 9 gets converted to ATP. 5.5 of that 9 is actually used for that plant. And 3.5 is available to be passed up the food chain to the next rung. So net primary productivity, it's abbreviated NPP, is gross primary productivity minus respiration. That equation does come up in tests. So gross primary productivity minus respiration is net primary productivity. This is the rate at which plants accumulate dry mass, biomass, the weight of the plant minus the water. It is measured in grams per meter squared. Anytime you see this where it's grams, meters, and then there's a negative exponent, that just means that the other way to write this is grams / meters squared. It provides for growth, maintenance, and reproduction of the plant. And this also includes all of the heat that's lost in the process of doing photosynthesis and cellular respiration. The remainder is deposited in around the cells as new material, and then it's available for consumers to eat. It's lost from food chains as it dies or decays. So if your plant dies before anything gets to eat it, we lose that energy, right? Net secondary productivity, or NSP, is the energy in the food eaten minus the energy lost in egestion, i.e. poop, minus respiration. So not all the energy taken in by the herbivores is made into new biomass, right? Think about how much a rabbit poops or how much guinea pigs poop. That's egestion. So they're like taking in this food and they can't digest every single part of it. So the cell walls and the stuff they can't digest is just pooped out. And any energy that went into building those cell walls and that stuff they can't digest is lost when the animal poops. And then cellular respiration doesn't harness 100% of the energy, right? It has a lot of heat loss. And so your NSP is really a lot smaller. Only plant material that passes through the gut is absorbed and used for life processes. Some's used for respiration, some's excreted as urine, some is stored in the body of the animal as fat. When we look at NSP, herbivores are about 40% of the energy, and they're gonna poop out 60%. They graze on static plants, there's low energy requirements. Carnivores are a little bit different. They take in 80% of the energy and they poop out 20. But remember, when you watch a lion eat a deer, they're not eating all parts of it, right? So of what they take in, they're only pooping out 80% because they're not eating the bones and they're not eating the fur and they're not eating the stuff that they know they can't digest. These numbers here are more realistic, but if you're ever asked like just a very basic food pyramid, it's that 10%. These are actually the more realistic numbers. So we have flows of energy and matter. Energy, there is a infinite amount of energy available in the environment because the sun just keeps beating down on us. It's available all at once, all the time. All organisms give out energy, and respiration releases heat, and it degrades as it goes up the food chain. Energy is temporarily stored as ATP. Matter, there is a finite amount of matter out here in our universe. It cycles and it recycles, and those are what we're going to look at here soon. All organisms release waste, nutrients, carbon dioxide, and water. That's all considered matter. It changes form, but it doesn't degrade. So we can change water from a liquid to a gas to a solid, and it's still water, right? It's just changing its shape. Long-term and short-term term for chemical storage is our stores. All living things are made of chemical elements, and we require 24 to be happy, healthy organisms, and they're in that image right there. This includes the big six: carbon, oxygen, hydrogen, nitrogen, phosphorus, and sulfur. So when we are to break down the parts of your body, it breaks down into these big six. Elements need to be available at the right time, at the right place, in the right concentration and form. If you take too much of a vitamin, especially one that's fat soluble, it is toxic. It can kill you. Too little, and you can have diseases from not having enough. So our first cycle that we want to talk about is the carbon cycle. Carbon is the building block of life and the element that anchors all of our organic substances. All of your big chemicals in your body are made with carbon because carbon can make strong covalent bonds. Organically stored with complex carbon molecules, organisms' biomass in the biosphere, when you die, it can be fossilized, and that fossilization then turns into fossil fuels over millions of years. Inorganically stored in simple carbon molecules like sedimentary rocks and fossil fuels, this will lock the carbon up for millions of years. Your ocean is a great carbon store. The carbon is dissolved into the water, or it turns into calcium carbonate in the shells of animals. We find it in the soil, and there's a very small amount up in the atmosphere in terms of carbon dioxide. Later today, you're going to be asked to draw your carbon cycle. Voila, here it is. The carbon budget is knowing that the amount of carbon in our environment is finite, but we are just changing where it's located and we're changing its form. And since the Industrial Revolution, we've taken a lot that was in the ground and we've put it up into the atmosphere. Well, the problem with it up in the atmosphere is then it acts as a greenhouse gas, as a blanket on our planet, contributing to global climate change. Nitrogen cycle. Nitrogen's needed to make proteins and DNA. It's the most abundant element in the atmosphere, but realize that the form that's in the atmosphere is not a form that you can take in. So it has to be fixed by organisms into a more usable form. Those organisms that fix our nitrogen are usually in symbiotic relationships in the soil, and they're usually with our legumes, so our peas and our beans and stuff. The stores for our nitrogen cycle are organisms, soil, fossil fuels, water, and again, the atmosphere. And here is the picture for your nitrogen cycle. Nitrogen is probably the most complex cycle because it's got all these terms. So nitrogen fixation is the conversion of nitrogen gas to ammonia ions. Nitrogen fixing free living bacteria will do this in the soil. Symbiosis and root nodules of legumes, like I said, peas and beans, will do it. Cyanobacteria, which is your blue-green algae in the top 200 feet of any body of water, will do it for us. And we also see cyanobacteria in our rice fields. Lightning will do it. That smell after a lightning strike is due to nitrogen fixation. And we actually have a commercial process that will do it, the Haber process. This is how we make fertilizers. So when you go to Green Thumb and you buy Miracle Grow. Nitrification, nitrifying bacteria convert ammonia to nitrates, and other bacteria convert nitrates to nitrates. Oh my gosh, it's like chemistry all over again. Nitrates are what's used and absorbed by plants for growth. Denitrification is removing nitrates from the soil. It's a reverse process, and it eliminates harmful animal waste. Decomp, dead organisms will supply nitrogen that's available to the plant for uptake because the nitrogen's already in the right form. This provides the bulk of nitrogen in the soil. And assimilation is just taking that nitrogen in to build complex molecules to make the plant bigger. So what's the human impact in the nitrogen cycle? Because there is a human impact. The use of fertilizers creates runoff. Runoff then creates eutrophication. Eutrophication is the process where there is bulk nutrients into a body of water and the algae goes, sweet, I've been waiting for this my whole life. And they grow really big and they reproduce really, really quickly, and they shoot right past carrying capacity, and then there's a massive die-off. When there's a massive die-off of all of that algae, then the bacteria come in, they're breaking it down. Well, in the process of breaking down that algae, they utilize all of the oxygen for the lake, which creates a die-off of the lake. All of the fish and everything else living die. Removal of animals and clearing of leaves and brush. So if, it's fall and you rake up all the leaves and you throw them into a plastic bag into a landfill, you've removed all of that nitrogen, as opposed to just letting the leaves lay there and decompose. If you let them decompose, then the plants that are going to grow the next season can use that nitrogen. Use of plants or animals for food. We lose the nitrogen in the sewage system. Every time you pee, you release nitrogen. And excess irrigation will wash it away from the soil into our bodies of water. Phosphorus cycle is always a test question, and here is the test question for the phosphorus cycle. Name which cycle does not go through the atmosphere. Phosphorus cycle is our only cycle that we're going to talk about today that does not cycle through the atmosphere. It's a major component in DNA, RNA, ATP, so we need it. And it cycles between the rocks, the soil, the ocean, the sediments, and living organisms. It has very low solubility in water. Most of it just drops down to the ocean bottom. And your major source of phosphorus on land is the weathering of rocks, and believe it or not, bat poo. So you can go to Green Thumb and buy a bag of bat guano, and the point of buying bat guano would be to get the phosphorus. Sulfur cycle is a component of proteins. Allows organisms to use your oxygen that you want to use. It's found in rocks and released into the soil and water through weathering. We also see it released in volcanic eruptions. So you're going to be asked to draw cycle diagrams. We are going to represent the cycles as a systems diagram. This is going to come back and back and back. Remember, a store, anywhere that chemical is going to remain for any length of time, is a box. And the flows are arrows. So as it goes from one store to another, you use arrows. We can calculate the rate of flux. This is the rate of transfer from one store to another. And we can also calculate the residence time. The residence time is how long is that water molecule in the ocean. How long does it stay there before it goes to the next store? Your source is the donating compartment and your sink is the receiving. Your source and sink can be a source and sink. So if you look here, this animal is a source of nitrogen when it pees. It is also a sink of nitrogen when it eats. So just depending on where the arrow is and what boxes we're going through as you follow the chain. When we talked about agriculture, assimilation and productivity is high here. Assimilation, what can I feed my cattle so that they're not pooping a lot? That instead of egestion, a lot of poop all over my field, that cow is instead keeping it all in and assimilating everything it eats and getting fatter and fatter and fatter. Because believe it or not, I want a fat cow because when I butcher it, that then becomes my profit. I can't make profit off of what the feed that goes into poop, right? So we want to make sure that we have high amounts of assimilation. And so we're going to alter our cow's diet to limit the amount of poop and increase the weight gain that's coming off of this cow. Human activities do impact our ecosystem when we talk about our cycles. Anytime you see the word anthropogenic, that's human activity. So anthropogenic whatever means that humans have impacted it. Humans tend to simplify the ecosystem for their own gain. We eat wheat directly. We, again, improve what we're feeding our cows so that we can get the most meat off of them. We try to maximize our net primary productivity by using artificial means to kill pests, fertilizers to maximize the yield. We talked in the last unit about the green revolution. An energy subsidy is additional energy added to our system beyond that which comes from the sun. All of our energy subsidency includes the human labor. Like I said, it's all of this to make our systems run more efficiently, to make sure when I grow corn that we get that corn for us to eat. It's all the fuel for our machinery that we're using. It's our water, it's our fertilizers that we're doing. It's the transport of this stuff from one location to another. It's the planting of the seed. As human population has increased, the need for more efficient food production has also increased, which means we need a higher energy subsidency. Humans subsidize all of this sometimes with water and wind and solar power, but we also have commercial subsidized in terms of fertilizers and fossil fuels. Yield ratio is measuring the energy in versus the energy out. In subsistence agriculture, 1 unit of food energy produces 30 to 40 units of food. So we have a high food production. In commercial farming, 10 units of food energy could produce as little as 1 unit of food. So what does this mean? Subsistence agriculture uses a low amount of energy, machinery, chemicals, and produces usually a high yield of food. But when we do commercial farming, because we've got all of this labor involved and all of this machinery and all these fossil fuels, we have a high energy input for sometimes very low food output. And that is it for today. You have survived another lecture.